Okay, let's go ahead and get started. So if you have read this introductory paragraph here, we are now considering sample distributions of a sample proportion. So previously we're given a sample and a mean, the standard deviation. Now we're going to be given proportions. So that is going to be given to you. If you look here, this symbol here is P with a little chevron over it. And we're going to call that P hat. Okay, so this little P here, that is P hat. And when we say we're considering a sample and the proportion of elements that possess a desired trait, that's a percentage. So we are dealing with percentages. So we say, okay, very simple way of putting that is 8 out of 10 people in a particular subset have brown eyes. Well, that's 80%. Okay, so that's what we mean by the proportion of elements possessing a trait. Okay, it's the percentage of those that trait, those people that possess that trait. Sorry. Okay, now we've got some new symbols here. So your keys right here. So you have P hat is your sample proportion, which basically X over N. Okay, X would be the number of people that have that trait, N would be the population. Okay, P is the population proportion. Okay, notice the difference here. So P hat is the proportion inside a sample, whereas P is the proportion inside the population. Okay, and then X is the total number of elements in a population, and that's a capital X. And then a lowercase x is the total number of elements in a sample that possess that trait. Same thing with lowercase n and uppercase n. And I promise you guys, it's not super confusing with them. You will see when we do some examples. And then Q is going to be 1 minus P. So remember that if some percentage of the population, so 80% of the population, has a certain trait, then you're going to have a percent of the population that does not have that certain trait. So that would be your Q. Okay, so that would be the 20% there. All right, so first formula here is the mean of a sample proportion. So the mean of P hat, okay, is just going to be equal to P. Okay, so all of the mean and everything that we're looking at, chapter 6 and 7, is always the same. So the mean of a population is equal to the mean of a sample, which is also going to be equal to the mean of a proportion. Okay, so the mean will never change that. Okay, the standard deviation, again, just like we looked at in 7.3 and 7.4, the standard deviation is what will change. Okay, so the standard deviation of a proportion, okay, that's standard deviation of P hat, is this formula here. So it's going to be the square root of P times Q over N. Okay, and then once we get the standard deviation for the proportion, then that's going to be your standard deviation in your z-score formula. Okay, so just like in 7.3, 7.4, in our z-score formula, our denominator changed. Same thing here. Okay. These ones are really easy to spot the difference here because you're going to be given a percentage, okay, as opposed to a mean and a standard deviation and all of that stuff. So let's look at some examples. So suppose the true proportion P of Americans over 25 years old that have a 4-year college degree is 35%. Okay, that's your percentage that have a college degree, which means that the percentage that do not have a college degree would be 65%. So we'll say P is 0.35, and Q here is going to be 0.65. Okay, they have to add to 1. Find the mean and standard deviation of the sample proportion for samples of the following sizes. So I have a sample size first of 38. The mean of P hat is going to be equal to the mean of the population, which is this 35% here. So that would be 0.35. Okay, so the mean of P hat is equal to P. The standard deviation is going to be given using this formula here. So the standard deviation of P hat is going to be the square root of P times Q. So we have a P of 0.35 and a Q of 0.65 over the sample size, which we're given here as 38. And I'm not quite sure why this is so small. Let me zoom in a little bit. Okay, so we're going to do that calculation, and we're going to use, let's do 4 decimal places here. So you can put this all in at once, or you can do it step by step. So let's say I do it step by step. I do 0.35 times 0.65. Then I divide by 38. And then I take the square root. So I would go second square root, and then just pull this answer. So second negative to pull the answer. I get 0.0774. Or if I want to put it all in at once, just make sure you're going to do a parentheses for your numerator. So in here, you're going to have parentheses, 0.35 times 0.65, and then divided by 38, close parentheses. Okay, should get the same thing. So that's going to give you 0.0774. Okay, let's look at this example here. So if I have a sample size of 75, the mean of p hat is still going to be the same. So just showing you guys here, it's not changing. The standard deviation, however, will change. So we're going to do the same calculation here, except now my sample size is 75. So 0.35, 0.65 over 75. And then take the square root. I think the biggest mistake that I do see students do is just forget to do the square root. So just make sure you do that. So there you're going to have 0.0551. So just make sure you try that in your calculator and you're able to get those values. And now we're going to take this and we are going to do a problem. So we have, if a sample of 75 Americans over 25 years old is randomly drawn, find the probability that over 40% of them would hold 4-year degrees. Okay, and that's based off of the information we're given up here, where in the entire population, 35% of Americans have 4-year degrees. So first you check, is NP greater than 5 and is NQ greater than 5? Why do we have to do that? Central limit theorem. Okay, remember central limit theorem. Basically, we need to have a big enough sample size in order to there we go. Big enough sample size in order to continue with the problem. So we have NP, the sample size is 75, P is 0.35. That's going to give us, let's see, no, 75 times 0.35, there we go. So 26.25. And NQ, 75 times 0.65, 48.75. Okay, so NP is 26 and change. We're just going to say 27. And NQ was 49. That really should be 26. Okay, so they're greater than 5. That's what we are concerned with. Okay, they're greater than 5. We can continue. All right, so we are asked to find the probability that in the sample of 75 Americans, 40% or more have college degrees. So what we're going to do here, first thing we're going to do is we are going to find, let's write this out for you, you're going to find your P, your P hat, and your standard deviation of P hat. Okay, so our P is the mean of the population, which was given to us as 0.35, way up here. P hat, okay, that is what's given to us in the problem. So that is 40%, so 0.4. And then the standard deviation of P hat is going to be the square root of PQ over N. Okay, so I guess suppose we could find Q as well, would be 0.65. All right, so here we would do standard deviation will be 0.35 times 0.65 over our sample size, which was 75. So we actually already did that right up here. That's that 0.0551. Okay, so first step, we find our relevant numbers. Second step, we are going to find the z-score. And I should have left you guys more room. I'm sorry about that. So step 2, you're going to find the z for this value. So that means you're going to do p hat minus p over the standard deviation of p hat. So p hat is 0.4, p 0.35, and our standard deviation we found to be 0.0551. Okay, so let's find that z-score. So 0.40 minus 0.35 divided by 0.0551. So that gives us 0.9074. All right, so we find the z-score. We are going to plot it on our standard deviation chart. So here's 0.9 close to 1, so maybe about right here. Okay, and what we want to do is we want to find the probability that greater than 40%. So we're going to be going to the right. So I'm going to shade to the right. So step 3, we will chart what we just did and find the probability. Okay, so we're going to find the probability. We can either look this up on the z-chart or we can use Normalcdf. And our lower limit will be 0.9074. And then our upper limit, since we're going to the right indefinitely, we're going to use positive 99. And if you have the 84, you're going to use a mean of 0 and a standard deviation of 1. So second distribution, Normalcdf, and then we have 0.9074, 99, and we're going to get 0.1821. Okay, so 0.1821, that is this area right here. Maybe I'll make this white here to right inside of here, if it will not erase it for me. There we go. Kind of hard to see. I don't know if I like that. All right, so what does that mean? So go back to your question. That means that in a sample of 75 Americans that we are randomly drawing over the age of 25, the probability that over 40% of them would hold 4-year degrees is about 18%. Okay, so that is your answer there. So probability greater than or equal to 40% hold a degree. All right, so give me a thumbs up, thumbs down, smiley face, something in the chat that you are okay with this problem. If not, give me a thumbs down or a frowny face, and then ask questions before we move on to the second problem. Okay, I got 1 thumbs up, 2. There we go. All right. Thank you, guys. Okay. All right, so B, we have another example here. So we've got, according to a university study, 1/3 of Americans believe that the next 5 years will bring good times. Assume that 33% of the current population of Americans hold this opinion. Let P be the proportion of a random sample of 800 Americans who are asked their opinion on this issue. All right, so we're going to pull out the relevant information here that we need. So let me, okay, so is NP greater than 5? Is NQ greater than 5? So we'll get back to that. We need P and Q to do that. So N is 800. P is going to be the proportion of Americans that believe that the next 5 years will bring good times. So that's a 0.33. Q, I'm going to go ahead and put over here. If P is 0.33, then Q should be 1 minus 0.33, so 0.67. Okay, now I can do the NP and NQ. That's a really big sample size, so we should be fine. 800 times 0.33 is 264. 800 times 0.67, 536. So we have a large enough sample size for sure. So 264 and 536. Again, that's all that's asking. Is my sample size large enough to proceed? You can still proceed, but if your sample size isn't large enough, then your study isn't really valid. Okay, so then here we want to do the standard deviation of p hat. So again, that is the square root of p times q. So we'll have a 0.33 times 0.67 over n, sample size 800. So let's find that. The square root of 0.33 times 0.67, close the numerator, divided by 800, close the square root. And I'm going to get 0.0166. Okay, so the standard deviation of p hat is 0.0166. We have our p is 0.33, and I think we've pulled out all of the information of this part of the problem that we can. So the actual question, find the probability that the value of p is between 0.35 and 0.37. So what is being asked here is that in this sample of 800 Americans, find the probability that the true proportion of Americans who believe this is between 35 and 37%. So between 35 and 37% of people say, yes, the next 5 years are going to bring good times. All right, so here we are being asked to find p hat, the probability that it is between 0.35 and 0.37. Okay, so notice here, just instead of x or x bar, it's p hat. All right, so first step, we find all the information we need, which we did. Second step, we need the z-scores for both of these values. Okay, so let's get those z-scores. We're going to use different p hats. Our p will be 0.33, and our standard deviation of p hat, 0.0166. All right, so let's see. Our first z-score is going to be 0.35 minus 0.33 over 0.0166. So that's going to give us 1.2048. Okay, then our second z-score, 0.37, we'll do 0.37 minus 0.33 divided by 0.0166. So 0.37 minus 0.33. So there you're going to get a 2.4096. Okay, then step 3, we will chart this. So here's 0 And we'll say 1.2 is maybe right here. And 2.4096 is maybe right here. And we want the probability, so we want the area or the percentage of the curve of the shaded portion. Okay, so we will go normal CDF, our lower limit 1.2048, our upper limit 2.4096. So let's go ahead and do that. Okay, so normal CDF 1.2048, 2.4096. So we get 0.1062. Okay, which is this area right here, which is the probability that the true population proportion of people that say that the next 5 years will bring good times is between 35 and 37. The probability of that is about 10%, 11%, 11% if you round it up. Okay, then step 2, or number 2, find the probability that less than 33% of the sample hold this opinion. So out of those 800 people, now the probability that it's actually less than 33%. So now we're doing the same thing, except with a p hat of 33. So the probability that p hat is less than 0.33. So if I convert this, step 2, to a z-score, I have a p hat of 0.33, a mean of 0.33, my standard deviation of p hat 0.0166. That's going to give me 0, because 0 divided by anything is 0. So really, that's just here. What is the percentage to the left of 0? Yes, 0.5. It's 50%. This is half the curve. So you really don't need to do any math here. It's 50%. All right, and then number 3, find the probability that p hat is greater than 0.38. So here p hat is greater than 0.38. All right, so again, we will convert the z-score, 0.38 minus 0.33. Our standard deviation, we're still using 0.0166. So that's going to give us 3.0120. All right, so on this curve, that's like way over here. I don't know why this is cut off, but it's not going to let me finish it. There we go. Okay, so that's like way over here, 3.0120, and it's greater, so it's going to the right. So it's going to be a pretty small proportion here. Let's go ahead and find that. We're going to go normal CDF with a lower limit of 3.0120 going to the right, so our upper limit is positive 99. So 0.0013. All right, so that is this value right here, 0.0013. So the probability that greater than 38% of the 800 people hold this opinion is pretty small. All right, and then I believe we have some practice problems. So let's do, what do we got? A, B, C, D, E. I'm just going to take a look through these. All right, so let's do the 3 practice problems, and then I'll let you guys do the classwork. All right, so for a population with the population size 18,000, a P of 0.25, find the Z value for each of the following for a sample size of 70. Okay, so here you've got a P of 0.25, which means our Q is 0.75. Sample size is 70. If we're going to find the Z-scores for each of these values, we need a standard deviation of P hat. So let's find that. So that's going to be P 0.25 times Q 0.75 over the sample size 70. All right, so square root of 0.25 times, not minus, 0.75 divided by 70 is going to give us 0.0518. All right, so for each of these problems, we're just going to change the p hat. Okay, so remember you're doing the z-score, p hat minus p over the standard deviation of p hat. So for 0.26, we're going to be doing 0.26 minus our p, 0.25, over 0.0518. So that should give us 0.1931. And we just want the z value here, so we don't need to go in and find any probabilities. And then we're going to do that for each of these. So everything what's going to change in each of these is just this part right here. Okay, so for 0.32, 0.32 minus 0.25 over 0.0518. So that's going to give us 1.3514. For 0.17, we're going to have 0.17 minus 0.25 over 0.0518. So that'll be negative 1.5444. And then last one, 0.20 minus 0.25. Over 0.0518. All right, so that's negative 0.9653. All right, let's look at the second problem. So according to the Bureau of Labor Statistics 2015 release, statisticians earn an average of $84,010 a year. Suppose that the current annual earnings of all statisticians has a mean of 84,010 and a standard deviation of 20,000. Find the probability that the mean earnings of a random sample of 256 statisticians is. Okay, so this is actually section 7.3, 7.4. Because, or I think it's 7.4, we're given a sample of 256, and we're given the value in numbers, not as a proportion. Okay, so we're not given a percentage of something. So this is going back to the sections that we did earlier this week. All right, so let's take a look at these problems. So find the probability that the mean earnings out of this sample is A, between 81,400 and 82,600. Okay, so first step, let's identify the values that we need. So we have that the mean of the sample is going to be equal to the mean of the population. That's that 84,010. We have a standard deviation of the population, 20,000. And let's see, we have a sample size of 256. And this is a sample, so we need a standard deviation of our sample, which, if you guys recall, that's the standard deviation of the population over the square root of our sample size. So the standard deviation of our population is 20,000 over the square root of 256 is going to give us 1,250. Okay, so now to find the probability that the mean earnings are between 81,400 and 82,600, we will convert both of these to z-scores. Okay, so that's the next step here. So let's see, our z-score for 81,400 will be 81,400 minus the mean, 8410, over our standard deviation of our sample, which is this 1,250. And then we're going to do that again for the 82,600. So I'm just going to write them both out. All right, so 81,400 minus 84,010 divided by 1250 gives us negative 2.088. And then 82,600 minus 84,010 divided by 1250, negative 1.128. All right, which means if I put this on a standard normal curve, so I'll draw a little curve over here. Here's 0, which means negative 1 is probably about right here. And then negative 2 may be right here. So I'm looking for this little area in here. So what I'm going to do to find this area is I'm going to go Normalcdf. And then I'm going to have a lower limit, negative 2.088, and an upper limit, negative 1.128. All right, so second distribution, Normalcdf, negative 2.088, and then negative 1.128. So there I've got 0.1113. Okay, so that is our answer. 0.1113 is this area right here, which is the probability that in the sample of 256 Statisticians, their earnings are between 81,400 and 82,600. Now for part B, are they less than 80,000? So let's do that part. We already have all the information. We just need a z-score for 80,000. So 80,000 minus 84,010 over 1,250. So that's going to give us negative 3.208. Chart that. Okay, that's way over here. And less than is going to the left. So it's going to be a very small probability here. Okay, when I do this in my calculator, I'm going to go Normalcdf. My lower limit will be negative 99. My upper limit, negative 3.208. So that's going to give us a very, very small number. So that's in scientific notation. So this is 6.7 times 10 to the negative 4. So let's just convert that. Okay, that means that this 6.7, this decimal place goes 4 places to the left. So 1, 2, 3, 4. That's what that is telling us. All right, so 0.00067. If I want to round that to 4 decimal places, 0.0007. So a very, very, very small probability that the statistician in this sample is, or any statistician in the sample is earning less than $80,000. All right, and then part C, let's go greater than 100,000. So same thing here. Find the z-score. So 100,000 minus 84,010 over 1,250. So that gives us a z-score of 12.792. Crazy z-score, right? So if I go over here on my curve, that's like way over here. And I want it greater than that, so that's like way to the right. That's going to give us a really, really, really close to 0 number. So let's go ahead and check that out. We would go Normalcdf. Okay, lower limit 12.792, upper limit positive 99. So I'm not going to bother drawing 38 positions on my on this paper here, but it's 9.4, and then that decimal's moved 38 places to the left. So it's 0. Okay, so this is 0. So there's a basically 0% chance that any of the statisticians in this sample of 256 are making greater than 100,000. Not saying that it's absolute 0, but it is a very, very small chance. 38 decimal places past or past 0. All right, how are we doing? We have one more problem here. So in some courses, students are graded on a normal curve. I have never done this. All right, so for example, students within 0.5 standard deviations of the mean will get a C. Between 0.5 and 1 standard deviation will receive a C+. 1 and 1.5 will be a B plus, 1.5 and 2, et cetera, et cetera. All right. So the class average on an exam was 60 with a standard deviation of 10. The bounds for a B grade and the percent of students who will receive a B grade if the marks are normally distributed are what? All right, so here, if I have a normal distribution curve, you've got a mean of 60 and a standard deviation of 10. So if I'm putting this on a normal distribution curve, here's my mean. So one standard deviation out would be 70, 2 would be 80, 3 would be 90, and then let's see, 50, 40, and 30. All right, so what we want to know are the B grades. So it's telling us here what we're doing here. So between 0.5 and 1 standard deviation of the mean is a C plus. Between 1 and 1.5 standard deviations of the mean receive a B. So this is what we want here, the B's. So 1 standard deviation of the mean is 70. So that is your lower bound. That's 1 standard deviation. 1.5 standard deviations of the mean is between 70 and 80. So right here. So what are those bounds? So if you got between a 70 and a 75 on the exam, your grade would be converted to a B. Okay, based off of this normal distribution curve. So it's the way the curve would be worked. If, for example, the mean of the test was fairly low and the teacher wanted to curve it. Okay, so kind of just based off of that, you'd have, and then the B plus would be 1.5 and 2, so then that would be 75 to 80 would be the B plus. And then you would keep going there, 80 to 85 would be an A minus, et cetera, et cetera. And then with the C's would be between 0.5 and 1. That would be the 65 to 70, et cetera. So that is how this works here. So you kind of just have to read through for the information, chart it. I always like to visualize it and then apply it. Okay, so all right, so now we have this class group work. Here's what I'm going to do is I'm going to let you guys work on this. I am going to stop the recording. If you want to stay and then go over it, we will do that. Otherwise, I'm going to record this and put it up as a separate recording. Okay, so this is the end of the recording for 7.5, 7.6. There will be a separate recording for the group work.